Okay, in this video we're going to explore some pretty important yet confusing terminology in probability theory, and some of that terminology you've already heard of before, and that's independent events. And we're going to contrast that with something that sounds similar but is very, very different, and that's mutually exclusive events. So remember, two events are independent if the occurrence of one does not affect the probability of occurrence of the other. And I'm sure you can remember that if you're flipping a coin 2 times in a row, you know the first coin toss has no effect on the second coin toss. So that's a great example of independent events. And remember, if you're calculating the probability of two independent events occurring, that's an AND statement. And if you're interested in the AND statement of independent events, all you got to do is multiply the individual probabilities together. The probabilities in isolation, I like to say. So the probability of A and B is simply the probability of A, just considered by itself, multiplied by the probability of B, considered in isolation by itself. And that implies that the probability of B is the same in isolation as it is following the event A. So the probability of B is the same as the probability of B giving A. And to contrast that with mutually exclusive, two events are mutually exclusive if they cannot both occur at the same time. So we're not interested in finding the probability of two mutually exclusive events occurring at the same time, because that's 0. We're interested in determining the probability of A or B, and that's our union notation. And remember, the connector there is, of course, an OR. And if we're trying to calculate the probability of two mutually exclusive events, we chain together two probabilities, again in isolation, but this time addition is the key operation. And that implies that the probability of both of these events occurring at the same time is absolutely 0. Okay, and help you get a better grasp of this terminology, let's look at an example, of course, where a person flips a fair coin and rolls a fair die. So what's the probability that she gets heads and a 6? So this first probability has an AND connector there in boldface type, and that means you should be trying to calculate the probability that both of these events occur. So of course the operation of choice there is multiplication, and you should be considering whether these events are independent or not. And the second probability is what's the probability that she gets heads or a 6? And I'm sure you notice the OR connector here. And if it's an OR connector, the operation of choice is addition and probability. So you're going to be adding some probabilities together, and you should be considering whether these events are mutually exclusive or not. Okay, so before we try to use our, fancier methods there of involving independence and mutually exclusive events, let's just list our sample space so we can be 100% clear what the correct probabilities are for both of those probabilities we're being asked to determine. So if we flip a coin, there's only two possibilities, heads or tails. And if we follow that coin flip or coin toss with the roll of a die, heads can be followed by the numbers 1 through 6, or tails can be followed by the numbers 1 through 6. And of course, your fundamental counting principle can help you predict the total number of outcomes in this sample space, which is 2 times 6, or 12. And here's the first 6 and the last 6. So once we have our sample space listed, whether we use that universal set notation or simply just a tree diagram with the outcomes listed, it's pretty straightforward to calculate the probability of getting heads and a 6. And you scroll through your outcomes and you look for heads, and you also look for a 6. So there's only one favorable outcome in this subset here of heads and 6 from the sample space. So there's one favorable outcome divided by the 12 possible outcomes. So we know with 100% certainty, using our sample space approach here, that the probability of getting heads and a 6 is 1/12. So now the question is there another way of calculating this probability in case our sample space gets a lot larger than just listing 12 possible outcomes? Well, if you're looking at an AND statement, first thing you should be considering is whether these events are independent or not. So the probability of heads and a 6 would be equal to the probability of heads followed by the probability of a 6 occurring on the dice, given that you have heads on the coin toss. And as soon as you write that out, you probably recognize that, hey, wait, that die is not going to care if a coin came up heads or tails. So yes, these are independent events. So you can lose that vertical bar notation there, which of course is used for dependent events. And all you need to do is chain both of these probabilities together, and thereby relying on the fact that these are independent events simplifies your approach just a little bit, but it still gives you the same answer. So the probability of getting heads on a coin is 1/2, and multiply that by the probability of rolling a 6 on a die, which is 1/6, and you can see that gives us the same probability of 1/12. And it's worth noting here that notice the first line in this slide, I set this up as possibly having dependent events. So even though I recognize shortly after that we have independent events, it's probably always a good place to start by just at least suspecting that these events might affect one another, again, when you're forming an intersection of two events, or the and statement and two events in a probability. Okay, and our last probability, probability of heads or a 6. And since this is an or statement, we get to any favorable outcome is going to be any outcome that has a head or a 6 in it, or possibly both, as we have just witnessed moments ago. So that means we can take those top 6 outcomes. Each of those have a heads in them. We can take the very last outcome since it has a 6 in it. And if note, we are also including the one outcome that is both heads and a 6, of course. So that gives us 7 favorable outcomes now. And we're going to divide that again by the total number of outcomes in our sample space, 12. So the probability of getting heads or a 6, this is a union probability, is going to be 7 out of 12. Okay, so let's see if we can calculate this or statement a slightly fancier way, again, in case we don't want to have to list out a sample space when it gets really, really super large. So what's the probability of heads or a 6? And remember, addition is typically the operation that should jump into your head immediately, and you should also consider right away whether these are mutually exclusive events or not. And of course, we just calculated the probability of heads and 6 moments ago. We know that it's not 0, so if you start trying to do this question, treating these events as mutually exclusive, you're going to get a wrong answer. And the reason this typically happens is that, again, that students think mutually exclusive is exactly the same thing as independence, right? And we know these events are independent, but that doesn't mean they're mutually exclusive. And we'll see at the end of this video, if you know your events are independent, well, that's actually evidence that you can't possibly have mutually exclusive events. So let's continue. We're going to calculate this probability, and you'll see that this is actually wrong, because remember, this is supposed to be a 7/12, and we're going to be close, but of course close isn't good enough. We want to be 100% accurate. So if we treat these events as mutually exclusive, because for some reason we're mixing up the terminology mutually exclusive and independence, we'll end up with a 1/2 plus a 1/6. And if we write that at a 12, so we can compare our correct answer, instead of 2/3, we'll write that as 8/12. We'll realize that's close, but it's wrong, because the correct answer that we got, relying on the safest of means by listing the sample space, was 7/12. So how did we mess this up? Well, remember, just because you have independent events, that's not the same thing as having mutually exclusive events. So we completely messed up the fact that our probability of our overlap is not 0 here. Remember, our overlap was 1/12. So if we take that 1/12 into consideration, that's of course the discrepancy between our wrong answer of 8/12 here, assuming that these events were mutually exclusive, probably because we already figured out they're independent and we confused that terminology. And if we take our intersection into consideration, we'll get the correct answer of 7/12. So let's have a look at that. Now here's the full rule of sum, as it's typically called in probability, and I'm sure if you look at that, it should look familiar. That's simply the principle of inclusion and exclusion, where we've moved away from the n notation of cardinalities now into the probability of each of those subsets occurring. So if we know that these events are not mutually exclusive because they are actually independent, that, as you will see in a few more minutes, rules out the possibility that these events are mutually exclusive. And we already saw that if we assume mutually exclusive, we get the wrong answer anyway. So basically, if you know your events are independent, do not assume they're mutually exclusive. You will be wrong. Make sure you include your overlap, of course, that probability of A and B in your union calculation here, or your or statement calculation of the probability. And you can list the individual probabilities. Probability of heads or a 6 is the probability of heads plus the probability of 6, but don't forget to subtract away the probability of heads and a 6, because guess what? You counted it twice, which is why we were 1/12 off in our last example. even though it was intentionally done incorrectly. So this is now going to give us a half plus a sixth, which is 8/12 minus that 1/12 gives us our correct answer. Okay, so one last caution on using the terminology mutually exclusive versus independent. Please be aware that mutually exclusive is not the same as independent. Independent events have no effect on each other, whereas mutually exclusive events must be dependent, since the occurrence of one event precludes the occurrence of the other. And while that might seem a little confusing, consider this. If you have events A and B and you know they are mutually exclusive, then as soon as A occurs, you know it's impossible for B to occur, because mutually exclusive events can't occur together. And hopefully that doesn't seem like independence to you. That's actually 100% dependence. You can't find events more dependent than mutually exclusive events, because one event can not just affect the other one, it can actually prevent it from occurring. Okay, so let's have one last look at our sample space here, and we'll organize it in a Venn diagram. So event A is tossing a fair coin and getting heads, and event B is rolling a fair die and getting a 6. So that will set up these subspaces where A is the 6 outcomes of getting heads on the coin. B is going to be the 2 outcomes where you get a 6 on the die. And that means there's only going to be one outcome where you can get both a heads on the coin and a 6 on the die. So once we know that our overlap has one outcome in it, we can subtract 1 from the number of elements in sets A and B and get 6 minus 1 for the A only section in our Venn diagram, and 2 minus 1 for the B only section in our Venn diagram. And if we add those numbers up, we get 7, so that means we're missing 5 more outcomes. And of course, that's the T outcomes and not the one that, of course, ends in 6. So that's the complement of our union. We're outside of our circles, and there's our 5 remaining outcomes. So our entire sample space is accounted for in our Venn diagram. And as soon as you have a Venn in front of you where there's a number, a cardinality in your overlap, then right away you know these events are not mutually exclusive. And that's one of the benefits, one of the many benefits of using a Venn diagram. But remember, just because these events are not mutually exclusive, that doesn't rule out the possibility that these two events are also independent. So when reading a Venn diagram such as this one, don't be too quick to jump to conclusions about independence. Of course, we can see that these events are definitely not mutually exclusive because the overlap is not 0, and that incidentally allows us to also calculate the probability of the overlap, which is the probability of heads and a 6, which is that green 1 divided by the total number of outcomes in the sample space. But this tells us nothing about independence until we visit the definition of independence in probability theory, which is the two probabilities multiplied together when they're calculated, I guess, in isolation. So from this Venn diagram, even though we've done this exact calculation previously in the video, I just want to tailor it to, I guess, reading the numbers off our Venn diagram here. And keeping in mind we're trying to find the overlap of heads and a 6. And in isolation, find the probability of heads and multiply it by an isolation probability of 6. So if we look at the heads circle, which is the event A, there's numbers 5 and 1 in there. So if we add those up, we get 6. And the probability of getting a heads then, from reading our Venn, would be 6 outcomes out of the total 12 outcomes, which of course does simplify down to 1/2, which we used previously. And similarly, if we look at the probability of getting a 6 from our Venn, we focus on the B circle and we add 1 and 1 together to get 2 and divide it by the total number of outcomes, 12. And we can see that that also simplifies to give us the more familiar 1 and a 6 probability of rolling a 6 on a die. And the product of those two probabilities is 12 out of 144, which reduces to 1/12, which matches the overlap probability that we calculated just reading our Venn diagram. So what does this mean? Well, it means our definition of independence holds. And since the probability of heads and probability of 6 multiplied together in isolation gives us the correct probability of 1/12, that's evidence that events A and B are independent. Okay, to conclude this video, let's summarize all our formulas involving and statements and or statements. So if we're dealing with and statements, of course, that's the intersection of A and B, and the probability of the intersection of A and B, if you have independent events, is simply the two probabilities determined in isolation multiplied together. And if you're at all uncertain as to whether you have independent events or not, then you better use this formula. So if you're calculating the probability of two events occurring, either in succession or simultaneously, then you better make sure that you consider the event A might have had some effect on B. Unless, of course, it's given in the problem that A and B are independent, and then you don't have to worry about it. And dealing with mutually exclusive events, well, of course, if you are calculating the probability of A and B, if you're working with mutually exclusive events, that's an easy one. That would be 0. But more typically, you're probably trying to calculate the probability of A or B, or the union of A or B. And if you have mutually exclusive events, you don't have to worry about the overlap at all, and you can just add together the individual probabilities. But of course, if there's any doubt as to whether you have mutually exclusive events, you better include that overlap and use the complete rule of sum as listed here once again, which of course has the subtraction of the probability of A and B. And that's to ensure, of course, that you don't include the probability of A and B more than once in your calculation. So in summary, when working with an and statement in probability, or the intersection of two events, always err on the side of caution and treat your events as being dependent unless told otherwise. And if you are trying to calculate the probability of a union of two events, or an or statement in probability, always treat your events as being not mutually exclusive and include that subtraction of the probability of A and B, again, unless told otherwise in a problem.